Hello, welcome to the NPTEL online certification course on deep learning. You remember that whatever we have discussed so far, that belongs to a class of the networks where the purpose was to discriminate among different categories. Or in other words, whatever we have learnt or the network has learnt, based on that, what the network does is, given an input image or given an input object, the network tries to classify that input image or the input object to one of the known classes or one of the known categories. So, the neural network or the deep neural network has learnt those different categories during the training process by means of a learning algorithm, which was back propagation algorithm, wherein the gradient descent operation was followed, where the gradient descent operation tried to minimize the loss function, where the loss function indicates that what is the accuracy of the decision that is taken by the neural network. So, during training, we give a pair, you give a training sample or the training data which is labeled data. So, at the output, you feed the data at the input and you find out what the neural network is giving at the output or what is the decision that the neural network is taking. And because we knew that what is the level of that particular data or what is the actual class belongingness of that particular data, so we can find out that whether that class belongingness and whatever the neural network was telling us was giving the decision whether these two decisions are matching or not. So, if these two decisions match, that is the actual class belongingness and the decision given by the neural network, if they match, in that case we do not need to train the network anymore, because the network is giving the correct decision. But in case the decision taken by the network does not match the actual class belongingness of the input data, then we have to train the neural network so that the error that you get at the output, that is minimized or the error is reduced to 0. And for that, the approach that was taken was gradient descent approach, and the algorithm was back propagation learning algorithm. And the networks that we have discussed so far, they are discriminatory in nature. So, what we are going to discuss today is what is known as generative model. So, unlike the discriminative model, in case of generative model, we give some description of the object or some description of the image, and we expect that the network will be able to generate or will be able to create the object or will be able to create the image based on the description which has been given. So, as we expect the network to generate the image, so the model is a generative model. And while doing so, we will try to see that a closely related network that we have already discussed before, which is an autoencoder. So, we will try to see what are the limitations of the autoencoder, and the particular generative model that we will discuss today is what is known as variational autoencoder. So, we will try to find out or we will try to discuss what is the difference between autoencoder and a variational autoencoder, and then we will discuss about an algorithm which is known as variational inference, which is used to train or which is the theory behind training of a variational autoencoder. And then we will also try to see that how the variational autoencoder can actually be realized in practice using the neural networks. So, let us first see that what is this generative model. Suppose we want the network to generate an image of an animal where we give some description of the animal. So, we say that it is a big animal. So, the animal has 4 legs, it has big ears, it has a long trunk, it has a pair of tusks and things like that. So, we can try to describe the animal with the help of these different attributes or these different descriptions. So, naturally, given this description that it is a big animal, it has 4 legs, it has big ears, it has long trunk, it has a pair of tusks, the kind of animal that will come to one's mind immediately that it must be an elephant. So, you try to draw the picture of an elephant, right. So, that is what is the generative model. You are giving some descriptions, and based on the descriptions, the model tries to generate an image of the animal, or the model tries to generate the object. And the descriptions that we are giving, these descriptions are what is known as latent variables. So, all these latent variables putting together, that becomes a latent vector or a latent descriptor of the object or the image. So, once we have this, as we have already shown before, that a closely related network that we have already discussed is what is the autoencoder, or we will say call it a traditional autoencoder. So, what this autoencoder does, given an input image or input data, the autoencoder maps this input data to a latent code via an encoder network. So, this encoder network is what we have shown over here. So, here what is shown is the encoder network. So, the autoencoder is generating a latent code, say vector z, through this encoder network, and then we have another network which is the decoder network, that is on this part. The decoder network regenerates or creates the input image or the input object from this latent or code that has been generated by the encoder. And you remember that when we talked about the autoencoder, we said that our purpose is that once you get a latent code from an encoder network, you simply forget the decoder part. So, this latent code is actually used for recognition or for classification purpose. The decoder network is used for training time only, when you train the autoencoder, so that your latent code becomes a representative of the input data. In order to ensure that, you use the decoder network. But once your autoencoder is trained, you simply forget about the decoder network. So, you simply use the input autoencoder, the autoencoder output, which is the latent code, and this latent code is later on used for classification purpose. And we have said before that we can have different types of classifiers which takes this latent input, this latent vector as an input, and gives its decision as to which of the categories your input data belongs. So, intuitively we can say that when this encoder is creating this latent vectors, it creates or creates the description of different attributes. Say that the attributes may be smile, it may be skin tone, it may be gender, it may be beard, whether the person is wearing glasses, whether the hair color is black, and so on. So, all these different descriptors or different attributes, for each of these different attributes, the autoencoder tries to get a numerical value, and this is generated during the training process. So, given such autoencoder, let us see that what is missing in this autoencoders. So, basically what the autoencoder is giving? Autoencoder is giving us a code for an input data, where this code is a compact representation of the input data. So, that using this compact representation, we can classify the input data. Whereas, what is required in case of generative model is, our generative model is not for classification purpose. So, in case of generative model, we need a latent space, so that we can sample a vector, as we can sample a code from that latent space, and we can get a realistic reconstruction corresponding to that latent code, which is given by the generator or the decoder. Usually, or in general, the autoencoders do not allow such interpolation in latent space, because the latent space which is generated by the traditional autoencoders are very sparse, they are not compact, or they are not continuous. So, these autoencoders are not really meant for generation or for creation of the images or creation of the data. They are actually meant for the classification purpose. Whereas, in case of a generative model, I want a decoder so that this decoder will get an input data, a code, a latent vector, and from that vector it can generate an output which will be a realistic object or a realistic image. So, what I mean is, let us take this particular example. Suppose I have an autoencoder model, and autoencoder, as we have seen, that the encoder part of the autoencoder gives you a latent vector or a code which is a compact representation of the input vector. So, suppose we train this autoencoder using a large number of say Barbie dolls and using a large number of say fish. Okay. So, when you go to latent space, suppose in the latent space all the Barbie dolls, they are coded in a space say something like this. Whereas, when you are training this autoencoder using fish, maybe you are creating a set of vectors somewhere over here. So, you find that in both these cases it is quite sparse. All the codes which are learned by the autoencoder, the codes are quite sparse. Now, what happens if I take a point somewhere over here? So, this gives me a latent code, and I feed this latent code to the decoder to reconstruct an image. Now, we find that in case of autoencoder, the autoencoder has never seen such a data. So, the autoencoder will be at loss to what is to create. So, that is why this big question marks. On the other hand, if I go for variational autoencoder, in that case what is expected of variational autoencoder is something like this. Because in case of variational autoencoder, it learns the distribution or the probability distribution of the vector z. So, I can have a smooth interpolation between any set of vectors. Okay. So, this is just an hypothetical example that maybe if I use a variational autoencoder, then the variational autoencoder will try to interpolate between the Barbie dolls and the set of fishes. Okay. So, somewhere over here it is in between fish and Barbie doll, and it may create something like a marbled, something like this. So, this is just an hypothetical example, and what I am trying to say is that what is expected out of a generative model, which in this case what we are discussing is a variational autoencoder. So, given this example, now let us see that why autoencoder cannot give us such a kind of reconstruction. See, autoencoders, what they are giving is, they are making us or they are giving us distinct cluster for each object class or each image class. So, as shown over here. So, you find that this is an output from the MNIST database, where the feature space or the latent vector space is a two-dimensional vector space. So, here you find that different numerals, MNIST database, if you remember, that those are database of different handwritten numerals. So, you find that when you train an autoencoder, the autoencoder gives you distinct clusters of the latent vector z for different classes. So, you find that for 1 there is one cluster, for 2 there is another cluster, and so on. And these clusters of these vectors are quite sparse. So, as these are sparse, it is not at all easy for a decoder to reconstruct, because if I take a point somewhere over here, as shown over here, if I take a point over here which the encoder has never seen, because the encoder has never seen this point or this vector, it is not possible for the decoder to reconstruct what should be the corresponding object or what should be the corresponding image. So, the decoder in case of autoencoder, what it needs is it needs a distinct code for each image that is to be generated. So, that is the limitation of the autoencoder. So, as the autoencoder gives you discontinuous latent space, so that means the decoder cannot reconstruct from such a space from a point which is actually unexplored. And if we sample from such points, the decoder may give us some output, it will give you some output, but the output may not be realistic at all. So, what we try to do is, our aim is that we try to make this latent space continuous, unlike in case of autoencoder where the latent space is not continuous, it is sparse. So, in case of variational autoencoder, what we try to do is, we try to make the latent space continuous, and though it is continuous, but still in this continuous latent space for different distributions of the latent vectors for different classes, they maintain their specific class identity or the class compactness. So, let us see what does it mean. So, what we want is that, unlike in case of autoencoder, where autoencoder gives you a deterministic latent code for every input data, in case of variational autoencoder, we are not interested in the deterministic code, but rather what we are interested in is to learn the distribution over the latent code. So, here instead of giving a unique code for every input data, we want to have the distribution of the latent codes for the class of input data that we have. For example, it might be more intuitive to determine a range of smile rather than giving a specific absolute value to the attribute smile, right. So, instead of deterministic code, if this distribution is, we assume it to be a Gaussian distribution, then for every class of input data or for every input data, instead of getting a deterministic code, we would like to have the mean and standard deviation for each component of the vector, the latent vector that you created. And we can assume that every component is independent. So, for a multidimensional case, what I get is a covariance matrix. The covariance matrix will be a diagonal matrix. So, this is what is expected out of a variational autoencoder. So, more specifically, taking this particular example, which gives you the difference between an autoencoder and a variational autoencoder. So, here you find that for the first example case, here it is quite apparent that this kid is not smiling, right. So, what the autoencoder, the traditional autoencoder will do is, it will assign a value which is negative, indicating that it is not a smiling face. What the variational autoencoder will do is, instead of giving a specific value to this particular attribute smile, it will give you a range of values, or it will give you a distribution of the smile variable. Similarly, over here in this second example, you find that the face is neither happy nor very happy. So, you can give autoencoder gives a distinct value which may be around 0 to this particular attribute smile, whereas the variational autoencoder gives a range of values with say mean 0 and the distribution of standard and the variance equal to 1. Over here, this kid is smiling a lot. So, autoencoder gives a positive value, assigns a positive value to this attribute smile, whereas variational autoencoder will give you a distribution with mean value which is positive somewhere over here, and it has a certain distribution. So, this is what your variational autoencoder gives, generates as a latent variable. It gives you a distribution. And once you have a distribution, now I can sample a vector from that distribution, and that vector is fed to the decoder for reconstruction of the image. So, now it is obvious that every input data is now represented as for every input data, the autoencoder, the variational autoencoder gives a probability distribution, and we can simply sample a latent vector from that probability distribution and pass this latent vector to the decoder for reconstruction of the image or the reconstruction of the object. So, this is what is expected out of autoencoder, variational autoencoder. And this particular diagram simply tells you that the encoder part of the variational autoencoder gives you the distributions of different attributes. From this distribution, you can sample a vector, the vector is fed to the decoder, and the decoder generates or the decoder reconstructs your image. And you find that your input image and the output image, they are likely to be similar because they have to belong to the same class. So, when you have this distribution of the latent variables, if I assume that it forms, it gives you a Gaussian distribution, then I will have a mean and a standard deviation. So, the mean of the vector, mean vector that controls where the encoding of the input should be centered around. So, it simply gives you the position of that particular distribution. And the standard deviation, obviously it controls the spread of that particular attribute, or it tells you the area or how much from the mean the encoding of that attribute should vary. And as the encodings are generated at random from inside a hypersphere, as we are assuming that it is a Gaussian distribution, what the decoder learns is not only that a single point within that space for which an image is to be generated, but the decoder learns that around that point or within a neighborhood of that point, there is a sample belonging to that class, and the decoder has to generate that sample. So, it is not from a single point within that hyperspherical space, but maybe within a neighborhood of any given point, it gets a latent vector and generates an output data corresponding to those vectors. So, now two things can happen. So, you find that we have two objectives. One is for every given data, input data, we want to generate a distribution. The distribution will have a mean and a variance. And we want that the distributions should be very compact, so that we can have smooth interpolation between samples, and the decoder can generate the corresponding output. So, for this possibly to make this smooth interpolation possible, the distribution should be quite compact. However, the mean and the standard deviation that the variational autoencoder learns, that may simply put the distributions of different classes far apart, or the mean vectors for different classes may be far apart. And if it so happens, then the interpolation might be difficult, right. So, what we want is, in order to make sure that the distributions become compact, they are not far apart in your feature space, in the latent space, you can impose a prior distribution. So, by asserting this prior distribution, we want that for every category of the objects for which we want the mean and standard deviation, so this distribution should be very close to a prior distribution, or in other words, we can measure what is the Kullback-Leibler divergence or KL divergence between these two distributions, and that KL divergence we will try to minimize. What is this KL divergence? The KL divergence between two probability distribution, it simply measures how much is the divergence between those two distributions, or we can simply put that it measures the distance between two distributions. We will see a bit later that what is the definition of this KL divergence and how we can compute the KL divergence. So, if we minimize the KL divergence, and in most of the cases what we do is this prior distribution that we impose, this is usually 0 mean unit variance or unit standard deviation. So, by minimizing the KL divergence, what we try to ensure is that the distributions of the feature vectors, the distributions of the latent vectors for the data belonging to different classes, they closely resemble that of the target distribution, where the target distribution is a Gaussian distribution or normal distribution with 0 mean and unit variance, and as a result they become very compact. So, the KL divergence loss, by minimizing that, it encourages encodings from different inputs to be clustered about the center of the latent space, because we have specified the target distribution to be 0 mean and unit variance, whereas the other loss, which is the data loss, that will try to maintain the clusters or the compactness of the cluster of the vectors belonging to the same class of data. So, we have to use both the KL divergence as well as the data loss together. If we use only one of them, if we use only KL divergence, then basically what we are trying to do is for the data or the encoding for different classes, we want all those encoded vectors to have 0 mean and unit variance. So, as a result, what will happen is the data will lose the structural property of the different classes. And if it loses the structural property, it becomes difficult for the decoder to reconstruct the data again. Whereas, if we use only the data loss, then the compactness of the distributions that we want in case of variational autoencoder or in case of generative model, that may not be maintained. So, if you use all of them together, so this example simply says, this diagram simply shows that if I only use the KL loss or KL divergence loss and I try to minimize that, then you find that the data belonging to all different classes, they are clustered together, all of them are combined together. So, as a result, you are losing the class identity or the structural difference between different data sets. So, this is what is not desirable. So, this is the one where if I put both the KL divergence as well as the reconstruction loss and the data loss together, the KL divergence will try to make the distributions compact, and the reconstruction loss or the data loss will try to maintain the class belongingness or try to maintain the separability of the data belonging to different classes. And that is what has been shown over here. You find that this set of data belongs to one class, this set of data belongs to one class, this set of data belongs to one class, whereas globally all these distributions form a very compact set of clusters, and that is what is required in case of variational autoencoder. This diagram puts all these different conditions side by side. So, on the leftmost case, what we have is what is given in autoencoder where you use only the reconstruction loss. So, by minimizing the reconstruction loss, the traditional autoencoder gives you a set of latent vectors where the vectors belonging to different category form different clusters, but the clusters are not compact in the latent space. The middle one shows if you use only the KL divergence loss, in which case the data belonging to different classes, they are all mixed together. Your cluster becomes very compact, but at the same time you lose the structural information. That means the different data sets, they can't maintain their own identity. So, as a result, this also becomes useless, because given a sample from such a kind of distribution to the decoder does not have any structural information, because all the structural information is lost. So the data becomes useless to the decoder. So what is required in our case is what is given on the rightmost one, that you try to minimize the KL divergence and the reconstruction loss together. So as a result, you get a compact distribution, whereas in every distribution, the identity of the data belonging to different classes, they are also maintained. So we'll stop here today. Today what we have seen is that what we can get from a traditional autoencoder, what are the limitations of the traditional autoencoder, why they cannot be used as a generative model, because traditional autoencoder gives you a latent vectors in a latent space, where the latent space is very diverse, it is not compact and it is not continuous. So as it is not continuous, if I sample a vector from that such a latent space and give it to the decoder does not know what to reconstruct or what to create. So in case of variational autoencoder, instead of generating a code for an input data, the variational autoencoder actually gives you a distribution of the codes or distribution of the encodings. So for reconstruction purpose, what you do is you sample a latent vector from that distribution and pass that latent vector to the decoder, and using this latent vector, the decoder can reconstruct a meaningful data or a meaningful image. So we'll continue more with this variational autoencoder or generative model in our next lectures. Thank you.